Okay, so in this video we are going to continue with SC13 and we're going to look at electroplating and we're going to look at alloys. I think you did look at electroplating a week or two ago in an interview lesson, but I will run through it again with you anyway. So if we look at what electroplating is, it's the use of electricity to cover one metal in a thin layer of another metal. Why would you want to do that? Well, for one, it can make things more attractive. So jewellery is a classic example. If you wanted to have a gold or a silver piece of jewellery, because gold and silver are quite expensive, if you had a ring made entirely of gold, it would be, really expensive. However, if you just had your ring coated in gold, it would look attractive, but it would be cheaper. It would also make it a bit stronger, but we'll look at that in a second. The other thing you can use it for is protecting against corrosion. So we saw in the last video that metals become weaker when they react with oxygen. To protect the metal from reacting with an element like oxygen, you can coat it in another metal that's resistant to corrosion. So chromium is an example there. It's resistant to corrosion, so you can coat vehicle parts with chromium to stop them getting weaker over time. I'm going to switch now to my exercise book. We're just going to go through how electroplating works. So if my aim is to coat a copper ring with silver, so I've got a copper ring, I want it to make it look prettier, so I'm going to coat it with silver. How am I going to do this? So we said it's the use of electricity. So just like with electrolysis, if I'm using electricity, I need a power supply. So I need a battery. So I'm going to draw my battery. And as before, I've got my positive end of the battery and I've got the negative end of the battery. The positive side of the battery is called the anode and the negative end of the battery is called the cathode. I've got a copper ring and I've got a piece of silver and I need to decide whether I put my silver at the anode or the cathode. Wherever I put my silver, I'll put the copper ring in the other place. So I want to coat my copper ring with silver. If I look at silver, I know that silver is a metal. And because it's a metal, it's going to be forming positive ions, and because it's forming positive ions, those positive ions will move to the negative cathode because opposites attract. So if I have silver in my setup, I know that the silver is going to move to the cathode. I know that I want my copper to be coated in silver. Therefore, if I put my copper ring at the cathode and I put my silver at the anode, so this here is my pure silver. If I put my silver at the anode and my copper ring at the cathode, what will happen is that the silver atoms will become silver ions. Because it's a metal, those ions will be positively charged. And all of those silver ions will move to the cathode, and in doing so, they will move to the copper ring, and you will coat your copper ring in silver. Now, in order for this to work, I need my system to be able to conduct electricity, so I need an electrolyte. Remember, an electrolyte is an ionic solution that can conduct electricity. So I need something for the current to flow through. There are a few different things that I can use, but just say I were to use something like sodium chloride aqueous, all right, something like that, or molten sodium chloride. Let's say it's molten sodium chloride. Okay, molten sodium chloride does conduct electricity, so it ticks that box. But if I'm using molten sodium chloride, I've got loads of sodium ions in my electrolyte, and my sodium ions are also going to move to my copper ring. So as well as having silver build up around my ring. I'm also going to have sodium build up around my ring. Okay, so for that reason, I'm not going to be using an electrolyte that contains a metal that's not silver. Okay, I want silver in my electrolyte so that the only metal moving to the ring is silver. So the electrolyte I'm going to use silver nitrate. That's the typical one that's used. And I can use aqueous silver nitrate. I can use it in solution as silver is less reactive than hydrogen, so silver will form at the cathode. So I can use silver nitrate solution as my electrolyte. Now you do need to be able to describe in detail what is actually happening. So that's what we're going to go through now. So we're going to start by looking at exactly what is happening at the anode. Okay, so I've said I'm attaching a piece of pure silver is being attached to the anode. So what exactly is going to happen there? Well, in my anode at the moment, when I've got my pure silver, I have got silver atoms. I've got silver atoms. But at the anode, my silver atoms are going to lose electrons. At the anode, oxidation always occurs, so my silver atoms will properly lose their electrons and become silver ions. So silver atoms lose electrons, that's oxidation, and become silver ions. Now remember, when you're losing electrons, you become positively charged. So if I wanted to write a half equation for that, I would start off with silver. And silver is a solid at room temperature, so this is a solid piece of silver. You're going to lose, and silver will lose just one electron. How do I know that? Well, actually, you can work out the charge on silver by looking at silver nitrate. So nitrate is an ion that you need to know. It's a polyatomic ion with a -1 charge. Silver, therefore, must have a +1 charge. So silver just loses one electron. When it loses that electron, it has a positive charge. And when it becomes an ion, it's no longer solid. It's dissolved, and I change my state symbol to AQ. It's aqueous. So the silver atoms, as soon as you turn on the current, they are going to lose their electrons because oxidation occurs at the anode. When they lose electrons, they become positive silver ions, and there's my half equation for the process. When they become positive silver ions, the Ag plus ions will move to the cathode. So all of those positive silver ions will move to the cathode. You'll also have the silver from your silver nitrate all moving to the cathode. What happens at the cathode? What happens when those silver ions actually get there? Well, when they get there, the Ag plus ions reach the cathode. And at the cathode, they're going to gain electrons because reduction always takes place at the cathode. And when your Ag plus ions gain the electron, they become Ag atoms again. So to write that as a half equation, I've got my Ag plus ions. When they're an ion, they're in aqueous form. They're going to gain the electron that they lost. And when they do that, they become silver atoms again, and they become solid. So what you'll see is solid silver forming around the copper ring. And it doesn't matter if it's the silver coming from the silver metal or the silver coming from the silver nitrate, that reaction is going to be the same. The ions arrive at the cathode, they gain their electrons, they become silver atoms once more, and when they become atoms, they become solid and coat the copper ring. The longer you leave the current to flow, the thicker the layer of silver on the copper ring. So if you just want a thin layer of silver, you'll turn it off quite quickly. If you want it nice and thick, you'll leave it on a little bit longer, and the silver will move across. So what you'll see here at the anode, you'll get the mass decreases. So just say you started off with 10 grams of silver at the start. At the end, you might only have 8 grams. As that silver moves across, then the copper ring, the mass is going to increase because the copper stays where it is, but you're getting the added mass of the silver. So if your copper started off at 10 grams, it might go up to like let's just say 13. So you might be wondering why I've called it 13 instead of 8. Remember, just say the copper gains 2 grams of silver from the pure silver, but it could also gain another gram of silver from the electrolyte. That's why I brought it the whole way up to 13, okay? These are just numbers I'm making up, okay? It's not accurate, but your silver the mass will decrease at the anode, and your cathode, whatever you've got at the cathode, the mass will increase. So if we look at some worked examples on electroplating, so I have this all done for you here in your booklet. If you look at some worked examples, why is electroplating used to make, really can't see that. Why is it used to make jewellery, okay? Makes it more attractive, and it's much cheaper than having the entire piece of jewellery made from gold or silver. So that's kind of why you use it. Describe how steel food cans are coated with tin and suggest why this is necessary. So this is just a 2-mark question, so you don't need to go into all of the equations. How can they be coated with tin? You can use electroplating. Why is this necessary? Because it stops the steel from rusting. Remember, steel contains iron. Iron can rust. You don't want it to rust, so you coat it with tin. Tin doesn't rust, it doesn't corrode. Metal bicycle parts are often coated in nickel to improve their appearance. Nickel plating metal is attached to the anode, and nickel chloride solution is typically used to the electrolyte. Write the half equations that occur at both of the electrodes, okay? So at the anode, you are starting off with nickel just as an atom. And what's going to happen is when it's an atom, it's solid nickel metal, okay? You need to work out how many electrons nickel loses by looking at the nickel chloride. Chlorine is in group 7 with a -1 charge. You needed 2 chlorine, so there's -2 overall. That must mean nickel has a +2 charge. So you have to use the formula of the electrolyte to work out the charge on nickel. It's a transition element, so you can't just look at the periodic table. So it's got a +2 charge. That means it's losing 2 electrons. So your solid nickel loses 2 electrons at the anode and becomes an Ni+2 ion. When it's an ion, it's aqueous. Then, when it's positively charged, it's attracted to the cathode. Those nickel ions arrive at the cathode. At the cathode, they gain electrons. So it's nickel gaining 2 electrons. And when it does, it becomes a solid again. Typically, the state symbols aren't required, but I have just included them there, okay? But at the anode, it's always something losing electrons. So whatever metal they give you is going to lose electrons at the anode. You just need to try and use the formula to figure out how many electrons they're losing. Once you get to the cathode, it's just the reverse of the equation. You're giving the ion back the electrons to form the atom again. So the 2 processes are just the reverse of each other. Just make sure you have them the right way around. Anode is oxidation, so they're losing electrons. Cathode, reduction, so it's gaining electrons again. They are the end of my worked examples, okay? So, have a read through this, nice and slowly. Make sure it makes sense to you. I know this is a little bit trickier, so if it doesn't, please message me on Teams, and then you can have a go at the exam questions underneath. This is the only bit of content in this topic that's potentially a little bit tricky. The rest of it is, again, nice and straightforward. So the last little bit we need to look at are alloys. Again, there's just a bit of content that you have to learn here. So an alloy is a mixture of one metal with one or more other elements. Now, that element doesn't have to be a metal. So it can be a metal mixed with another metal, or a metal mixed with another element, okay? But you're mixing them together. It's a mixture. It's not a chemical reaction, so it's not a compound. 2 metals won't react with each other, but you could mix them together. So steel, we've mentioned steel before, it's an alloy made of iron and carbon. So you mix iron and carbon together to make steel. In bronze, you mix copper and tin. You're not reacting copper with tin because 2 metals won't react, but you can mix them together. And then brass is made of copper and zinc. You don't need to specifically know the alloys and what they're made of, apart from steel. You do need to know that steel contains iron. Alloys are stronger, they are less malleable than the metals they contain, and you need to be able to explain why. So I've got a diagram here. So here I have got a pure metal, and metals are solid, so the particles are arranged as they would be in a solid in a nice, neat layers. So we know that in a metal, those particles are actually positive ions, and the layers can slide over each other. Because those layers can slide, we say that the metals are malleable. So if you got a hammer and gave it a whack, those layers of the metal ions would just slide over each other, and then we can say that they are malleable. If you have an alloy instead of a pure metal, then you're going to have some of the atoms. You might have an atom in there that's different sizes, and that disrupts the layers, and the layers can no longer slide over each other. So if you were to whack this with a hammer, you'll see that because you've got this different sized atom in the center, it disrupts the layers cannot slide, and it makes it less malleable. So they're less malleable and ductile, which means they're harder to hammer into different shapes, but it does mean they're a lot stronger. So if you want something to be super strong, you don't want it to be able to change shape, then you're going to want an alloy. If you're trying to mold something into different shapes, then you're going to want to use the pure metal. So you do need to be able to describe why pure metals are weaker than alloys, or why they're more malleable. We now need to look at steel. Okay, there are a couple of different versions of steel. All steels contain iron, but you're mixing iron with different things. So you've got mild steel, which is iron with just a small amount of carbon and manganese. Then you've got tool steel. You mix iron with tungsten, another transition metal, and molybdenum. And then stainless steel, you mix iron with chromium. So again, you don't need to learn the different types of steel and what they contain. You don't need to learn that off by heart. You just need to be aware that there are different versions of steel. They all contain iron, but you mix them with different things. So because you're mixing them with different things, they do have different properties and therefore different uses. So your mild steel, with only a small amount of carbon and manganese, it's stronger than iron alone, for the reasons we talked about up here. Having carbon and manganese will disrupt those layers. It makes it stronger than iron alone, but it is still malleable and can still be used for building material. It can still be shaped. If you've got a higher strength steel, you put way more carbon. So you basically really disrupt the layers, make it very difficult to mold them into shape. And you would use something like that for steel girders and roll bars. I don't know what steel girders and roll bars are, obviously terms from construction, but they need to be strong. And then you've got stainless steel that contains chromium. So we've come across chromium before when I mentioned electroplating. Chromium is resistant to corrosion. So if you put chromium and mix that with your iron, chromium can form a tarnish, and that prevents the iron from rusting. So iron itself, iron alone, will react with oxygen, it will corrode and become weaker over time. You mix it with chromium, the chromium will react with oxygen, but it will form a tarnish, and that tarnish will protect the rest of the iron. The tarnish that chromium forms, unlike copper, which formed a green layer, chromium forms a thin, transparent tarnish, so the metal will still look shiny even after that tarnish is formed. So again, you don't need to learn off the different types of steel and what they contain. You just need to be aware that there are different alloys of steel. They all contain iron, but they've got different properties and therefore different uses. So I've got one or two worked examples here. Why are car parts made from alloy steels rather than just pure iron? Alloy steels are stronger. They're also lighter than pure iron because you're mixing the iron with lighter elements. It makes them lighter overall. So they're stronger and lighter. Why is stainless steel used for surgical instruments? We just said that stainless steel contains chromium. It cannot rust. Okay, you don't want your surgical instruments to rust. So try and pick out a property that will be particularly important for that function. With surgery, you don't want them to be able to rust. The last little bit, I'm not going to go through all of this because a lot of it is self-explanatory. You'll be able to read it for yourself. But I've got a list of metals, so aluminium, copper and gold are metals. And then at the end, I've got 2 alloys, so magnesium, which is made of aluminium and magnesium, and then brass, which is made of copper and zinc. I talk about the properties and then I talk about their uses. So for example, aluminium, really good at conducting electricity, and it resists corrosion, and it's cheap and strong, therefore it's perfect for overhead wiring. Copper is used for wiring in general, but it's not as cheap as aluminium, it's not as strong as aluminium, so you just use it for wiring in appliances rather than the overhead wiring. Gold, again, it's a really good conductor of electricity, but it is expensive, so you only use it in small parts in electrical goods. You also use it for jewellery, and then yeah, the rest of them you can. So brass, for example, good conductor, not as good as copper, but it's really strong. So you put brass in the pins of plugs in case you stand on the plug or you damage the plug. Brass is stronger. So just have a read through that table, okay? And then these are the typical questions that you might get asked. So they'll give you, properties of gold. It's ductile, it's a good conductor of electricity, so why then do you prefer copper? Well, copper has those properties too, and it's cheaper. So if you read through them, I'm not going to go through all of the worked examples with you, okay? If you read through them, a lot of it is just kind of applying common sense. So again, you're not just being tested on your ability to recall information. Typically, they'll provide you with the properties and the uses in the question. What they want you to do is link the property to the use and explain why that metal is suitable for the use because of the property that it has. So I've gone through a few examples there of the typical questions that you might get on the uses of alloys and metals. I think it should be self-explanatory when you read through them. Once you've gone through that, you've got the exam questions. So I've pulled out all of the exam questions on this topic from the last couple of years. So the exam questions are there. You can fill the answers into your booklet, and then at the end you have got the mark scheme, so you can mark your work once you're done. You've also got additional guidance, so you should be able to use these mark schemes. They're nice and detailed to mark your work. You've got 2 cover lessons to do this. That should be plenty of time. There's not that many questions, so you can also use your lessons to learn the content, familiarise yourself with the content, and then use the exam questions to almost test yourself. Because there's less written work this week, I do expect you to be able to complete all of the written work in the cover lessons, which means I'm also going to set you a quiz on a carousel, not just on show my homework, because I want you to actually write in the answers, not just do multiple choice. So I just want you to complete that quiz for me just so I can see how you are getting on in lessons. So when I set it up, I'll give you the option of revision mode, so you can basically learn the answers to the questions before you attempt the quiz if you feel you need to, and you'll have 3 attempts to complete the quiz. So that will all be due for next Wednesday. Again, if you've got questions or problems, please just message me on Teams. I'm really sorry that I'm not in at the moment, but just message me on Teams if you need help, and I will help you out.